No, it's equivalent to, it's 10 million times smaller than an atom and 100 times smaller than a proton.
1/100th the diameter of a proton. Meanwhile, all the world is vibrating because everything is at a temperature. And cool it as much as you want, there's still vibrations. And somebody is walking down the street. I remember being on campus there. Can I call it a campus? That's what it was. And you can detect cars on the road a mile away. You have to insulate this. That's half the science done for the experiment. You should get a Nobel Prize for that.
Well, that's what the Nobel Prize was given for. For that, yeah.
To have successfully isolated the effect you're trying to measure.
So why do the universe's most violent acts announce themselves as the faintest shiver of space? And what does it demand of us to truly listen? It feels backward at first. When black holes, the mass of stars, slam together, you imagine a thunderclap that rattles every atom. Instead, space-time itself flexes by a fraction that barely nudges a laser beam across an observatory's arm. The reason is not that the event is small, it's that space is stubborn. To stretch the fabric of space-time takes an absurd amount of energy, and even when titans collide, converting several suns' worth of mass into pure gravitational radiation, the resulting strain, by the time it traverses hundreds of millions of light-years, is on the order of 1 part in a billion trillion. Space yields, but only a little. The signal arrives, not as a shove, but as a tidal whisper, changing the length of a 4-kilometer tunnel by far less than the width of a proton. That mismatch between cause and effect is the challenge and the invitation. Because once you aim to catch a whisper, you discover how loudly the world hums. The ground sways with ocean waves that break thousands of miles away. The air molecules jostle and clap against mirrored surfaces. Thermal jitter wiggles the very atoms of the glass. Your detector is not on Earth. It is of Earth. Every heartbeat within it is recorded. So, the strategy flips. You don't amplify the cosmos, you quiet ourselves. Suspend mirrors on multi-stage pendulums so that the Earth's grumbling dies out before it reaches the optics. Evacuate the tunnel so light can travel unbothered. Polish the mirrors until the surface deviates by less than the size of a virus. Then, you learn a deeper lesson. There's a limit to how still can be. Even in the deepest vacuum, even cooled near absolute zero, the vacuum itself fluctuates. Photons arrive with randomness. Shine more light to reduce that randomness, and the photons push back on the mirror with their own jittering pressure. You've traded one kind of uncertainty for another. That's not a failure. It's physics telling you how to play the game. The quantum world gives you a budget of certainty. Spend it on the quantity you care about. You can inject squeezed states of light, engineered ripples of the vacuum, so that the phase of the light becomes more certain, tightening your grip on distance while allowing other properties to fuzz out. You can shape the response of the detector so that the unavoidables slide past and the inevitables stand still. In that optimization is a quiet triumph. We've learned not only to measure nature with extreme delicacy, but to sculpt the very noise that once defied us. It's a strange kind of alchemy where ignorance is redistributed, not eliminated, and where progress is measured in decibels of quiet. But even if we can pull a signal from the murk, why chase it in the first place? The answer is that a new sense is always worth cultivating. Gravitational waves do not bounce off gas or dust. They do not scatter in electromagnetic fog. They travel straight from the source, bearing the imprint of the last few orbits before impact, the final cries of objects no light can escape. From those timetables and tones, we can weigh black holes with the accuracy of jewelers. When neutron stars spiral together, we can watch matter so dense that a teaspoon would outweigh a mountain, squeezed and torn until nuclei dissolve. In that same cataclysm, neutron-rich debris is flung outward and undergoes rapid neutron capture, forging many of the heaviest elements while the blast floods space with light and, likely, neutrinos. Some of the gold in your wedding band and trace metals in your electronics were created in kilonovae that flare blue at first and then fade to a deep red. The shape of the wave encodes distance directly, so without a single standard candle, you can establish how fast galaxies recede. And every event, logged with patience, maps a population. How often the universe used to make these pairs, how galaxies assemble their dark hearts, how gravity behaves when space curves so sharply it nearly folds into itself. Then the scale shifts again. There are waves not from single cataclysms, but from countless giants murmuring at once. Throughout the cosmos, supermassive black holes and the cores of galaxies waltz on orbits that take years to complete, emitting waves as slow as the sweep of a minute hand. You cannot build an interferometer large enough to catch them in the same way. So, you let the galaxy help. Use millisecond pulsars, spinning neutron stars whose beams flash with atomic regularity as metronomes scattered across the sky. If space-time swells and shrinks between us and them, their ticks arrive early or late by billionths of a second, correlated across the heavens. Recently, those correlations began to emerge, a background consistent with a vast population of awakening black hole pairs, and maybe, just maybe, other exotic sources waiting their turn. Meanwhile, a planned observatory in space, a triangle of spacecraft millions of kilometers apart, will float in quiet sunlight to sense waves in the millihertz range, from compact binaries and perhaps the tremors of the early universe. What started as the smallest motion we could imagine is becoming a spectrum, like hearing not just a note, but an orchestra. There's a moral here that extends beyond instrumentation. To learn anything subtle, you must not merely look, you must subtract. You chip away everything that is not the phenomenon until what remains is the thing itself. That's true in the lab, where isolating the target effect is not ancillary to discovery, it is discovery. And it's true in thought, where clarity lives on the far side of distraction. We commonly think of science as the art of building, bigger telescopes, bigger colliders, bigger data. But in this case, the victory was a practiced absence. Fewer vibrations, fewer uncertainties, fewer assumptions. It took decades of engineering just to make a room quiet enough for the universe to be heard. And when it was, the first sound we caught was not a random buzz. It was a rising chirp, a cosmic crescendo that started at the low edge of human hearing and swept upward as two black holes pirouetted toward union. That note was inevitable, dictated by general relativity's geometry, written into the curvature of space itself. We didn't impose it, we got out of its way. So why are the universe's loudest dramas encoded in the tiniest motions, and what must we do to hear them? Because gravity speaks softly across great distances, and space-time resists deformation with a tenacity that reduces even cosmic violence to a gentle strain by the time it arrives. To hear that softness, we learn to hush everything else, the ground, the air, the heat, even the quantum jitter of light. In the process, we gain not only measurements but a new way of knowing, one that prizes patience over force, precision over spectacle. When we practice that discipline, the faintest quiver becomes a story of colliding worlds, the hum of 1,000 galaxies, and perhaps someday the afterglow of the universe's first moments. The cosmos did not hide the message to taunt us. It's simply how the laws are written. Understanding them requires us to become quiet enough and clever enough to let the world tell us what it already knows. Like if this was interesting and hit the subscribe for more,